Hi, this is the homework review of the new way we're doing chemistry. This is section 1. I'm going to attempt to explain the answers, not just give you the answers. So hopefully it will be a little bit more understandable. Please bring any questions you have to class on Monday. These are the elements that you need to review for the test on Monday. Fluorine, F, aluminum, Al, carbon, C, chlorine, Cl, copper, Cu, gold, Au, helium, He, hydrogen, H, iodine, I, iron, Fe. Remember, the first letter is always capitalized, and if there is a second letter, it is always lowercase. A tour of the periodic table. Down on the bottom right, periodic table for your reference. Number 1, on the periodic table, periods are horizontal and the groups are vertical. So an example of a period would be your hydrogen, helium would be period 1. Period 2 would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And then your groups are going to be your vertical. So those are those columns. And you're going to have, each of those have a name, just like was in the video. And we'll need that answer in a little bit. But to refresh you, group 1 is this hydrogen group. Group 2 is beryllium. 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 are that metals group in the middle. And then you have 13, 14, 15, 16, 17, and 18 there on the right block. What group does fluorine, chlorine, and bromine belong to? That's that group 17, column 17. And they're the halogens. You need to know some of the other groups that are on here, and just as a refresher, that metals group in the middle, you have your non-metals, and so on. You need to review those from the video. How many valence electrons would group 17 have? If you count them, hydrogen is going to have 1 valence electron, that column, 2 in the beryllium column, 3 in the boron column, 4 in the carbon column, 5 in the nitrogen column, 6 in the oxygen column, 7 in the fluorine column. So there's going to be 7 electrons there, and then 8 in the helium column. What elements make up the noble gases? You have helium, neon, argon, krypton, xenon, radon, and they have the 8 electrons. And then what elements are crucial for all living things? That would be your CHNOPS from the video. You have your carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium, and then your hydrogen over here. And you can see them color-coded. Atoms in the periodic table. What do the following things tell us on the periodic table? The atomic number, if you look down at this square in the bottom, you're going to see atomic number is the number of protons in the nucleus of the atom, and that number is going to be the number position on the periodic table. So carbon is 6, and it has 6 protons. The mass number, the atomic mass, is the number of protons plus the number of neutrons. And the reason it is not an even number is, remember, it is a weighted average of the different isotopes. How do you know how many electrons an atom has? It's going to be the same as the protons, or the atomic number. And the only time that is different is when it is in a molecule format and it is borrowing or lending its electrons. What determines how an atom behaves? The number of electrons in the last valence shell is how you're going to determine how an atom behaves. So hydrogen and everything in this column is going to behave like it has 1 electron and 1 electron to lend. the 1s and 2, the elements in column 2 are going to behave like they are happy. They're going to have that full S shell. So they're going to have two electrons. So they're not going to want to really lend as much, but they could. And then I used this element chart so that you could see where that F block fits in. And you can see here that all of these metals and then that lanthanide and actinide series, they are all going to be very different. It all depends on how protected those inner shells are, on whether or not they're willing to lend out those electrons or borrow electrons. And then as you get closer to the right side, you get ones that are more willing to accept electrons to complete their outer shell. And then on the far right, you have your noble gases, which are perfectly happy. They have very full p block shells, and they are very, very stable, very unwilling to lend or borrow. Okay, molecules and elements. Again, we have our periodic table in the left corner. So you're going to have what elements make up the molecule water. You have 2 hydrogen and 1 oxygen. And we're going to go over what is the average mass of 1 mole of water. So when you look at it, we're going to figure out where hydrogen and oxygen are on our chart. And you can see here that we have 16 and 1.008 for our atomic masses. So where that's going to fit in is hydrogen is 1.008 and oxygen is 16. So if we're trying to find the average mass of 1 mole of water, this is the number of grams per mole. So 1.008 grams times 2, because we have 2 hydrogens in water, is 2.016 grams. And then you have your 16 grams plus 2.016 grams equals 18.016 grams per mole. And that is the final answer on that. So in order to find average mass of whatever the chemical is, you need to know what it is made of, and then you can figure out from there how much 1 mole weighs based on the periodic table. Chemical analysis. We will use the periodic table on the left to help us answer the questions. What are we looking at when we do chemical analysis? We're looking at compounds. Elements can be very easy to identify, to tell apart. We have tests that are very good at telling us if we've got an element versus a compound, and then you need further chemical analysis to find out what is in a compound. What is the atomic mass of 1 mole of gold? Well, if you look up here at the periodic table, number 79, AU, 197.0. Again, atomic mass is going to be 197 grams per mole. Using this data, can you identify the composition of ethanol? Well, let's figure it out. We are given these elements using these numbers up at the top. We're going to do the work like they did in the video. So this data tells us how much carbon came out, hydrogen, and oxygen. So we need to start with finding out hydrogen and oxygen. How many moles is in each of these? So carbon is 12.01 grams per 1 mole. Hydrogen, 1.01 is what they used for this specific experiment. So that's why the number is a little different. So we're going to go round that one up to 1.01 grams. And then oxygen was 8.00 grams. And oxygen is 16.00 grams per 1 mole. So when you do all this, you get 1/2 mole. We get 3 moles of hydrogen, this one is oxygen, and then we get 1 mole of carbon. Well, since we can't have, this is how it would look, carbon, hydrogen, oxygen, and again, since we can't have half a mole, we need a whole number, we need to go ahead and multiply that through by 2. So we would have 2 carbons, we would have 6 hydrogens, and 1 oxygen. And this is the chemical formula of ethanol. And using the data, can you identify if the ethanol is pure? Since there are no extra elements included in this mass spec identification, we're going to assume that it is pure, especially since the numbers came out exactly to what is known about ethanol when you go and verify it by the data done by other scientists. Okay, the mole. We're going to need the periodic table again to answer the questions for this homework. What is Avogadro's number? Avogadro's number is a constant defined as 6.02 times 10 to the 23rd, and the definition of that is how many elements, molecules, particles are in 1 mole. What is the AMU, or mass, of 1 mole of nitrous oxide? So to find that out, we would need to look at nitrogen and oxygen on the periodic table, and you see their atomic weights there. And what you're going to do is add those together because we have 1 mole of each of those as designated by the formula, and you add them up. 14.01 grams plus 16 grams equals 30.01 grams per mole. Simple as that. So, how many particles of hydrogen peroxide, H2O2, is in 12.3 grams? So, we're going to put these together. First, we start off with defining hydrogen and oxygen. We need to know what the atomic weight is of hydrogen peroxide. So hydrogen, when you come here and look at the weight on the table, it's 1.008, and we need 2 of those. So we get 2.016 grams. And then for oxygen, here, it's 16.00 grams times 2 is 32.00 grams. Then you're going to add those up, and we get 34.016 grams per mole of H2O2. Okay, so that number is going to be important as we move forward, because we want to find out how many particles are in 12.3 grams. So we have 12.3 grams. I'm going to write our bridge notation out. So we know how many grams are in 1 mole. .016 grams are in 1 mole. And we know how many particles are in 1 mole. In 1 mole, we have 6.02 times 10 to the 23rd molecules. And so from there, we can find out what the number is because we can put it in our calculator. And I do 12.3 times 6.02 times 10 to the 23rd, and divide that by 34.016 is equal to 2.17 times 10 to the 23rd molecules. And that's the answer. Okay. Do a little erasing on this guy. Okay. How many particles are in 5.72 grams of C6H12O6? So we start off with defining carbon is 12.01 grams, and we have 6 of those. We have hydrogen is 1.008 grams, and we have 12. And then oxygen is 16.00 grams times 6. I can put all of these numbers into the calculator. So 12.01 times 6 is 72 grams. 1.008 times 12 is 12.096 grams. 16.00 times 6 is 96 grams. And then add all of that up. 96 plus 12.096 plus 72 C6H12O6 is 180.096 grams per mole. Okay, and then we put that number into the system. So 5.72 grams. And we know that 180.096 grams goes into 1 mole. And for 1 mole, we have 6.02 times 10 to the 23rd molecules. So 5.72 times 6.02 times 10 to the 23rd divided by 180.096. That is going to equal 1.912 times 10 to the 22nd molecules. And that's it. Coulomb's law. Coulomb's law states that if you have opposite charges, they will attract, and two similar charges, they will repel, and that is true. That is the basis of how we learned about magnets and magnetic fields. What can we use Coulomb's law to predict? That would be the ionization energy, and we'll go over that in a second. What kind of instrument did Coulomb use to measure ionization energy? And that was the torsion balance. PhET. That was the program. I wanted you to go and build an atom. Take a picture with your phone or screenshot it and tell me about the atom that you made. You were going to add neutrons, protons, and elements, and you could see how things changed by adding those. When lithium is shot with a PES, why does it have two peaks? Well, when we look at this, it's the yellow line, and the first peak is, and you're going to read this one from right to left, so the first peak is the ionization of the outer electron shell, and the second peak is the ionization of the inner electron shell. And when you look at lithium, you can see that it has 3 electrons, and so the outer electron shell, this first peak, 1, is going to be this free electron leaving. This bigger peak, 2, it's later. It takes more energy to release these two, and they're a bonded pair. There's 2 of them, so it's a bigger peak than these other ones. So that shows you how many electrons are actually being released. Electron configuration. Does hydrogen or helium have a higher first ionization energy? Helium, because more positive pull on a single electron. Remember from the video how there are more protons, there are 2 protons in helium, and there's only 1 proton in hydrogen. So there is more positive pull pulling on those electrons. How many orbitals and how many electrons does each of these electron shells have? So here we have shell S has 1 orbital and it has 2 electrons. P has 3 orbitals and 6 electrons. D has 5 orbitals and 10 electrons. And F has 7 orbitals and 14 electrons. And those are orbital slots. They're not number of shells because these are positions within the orbitals. Okay, I wanted you to write out the diagonal chart for writing electron configuration. And here it is to the right. Remember 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14. And you can see those numbers reflected here. Those electron numbers for the shell are over here in the energy levels. And the reason we write it this way and then we write the diagonal lines is because of how we end up writing out the periodic table to give us our electron configuration for each of these numbers. So hydrogen would be a 1s1 and helium would be a 1s2. And you can see as you go through here that if you figure out where the position is on the periodic table, you can then use that to help you figure out how to write your configuration. So chlorine is position number 17. It has 17 electrons. And so your end result should add up to that number. So when we fill it out, 1s2, and then following the diagonal, 2s2, and then 2p6, 3s2, 3p, and 5. Because if you go 3p6, that's 18 electrons. So we'd be 1 short. Silver is 47 electrons, and I wrote this one as the noble gas configuration. So it starts with krypton, and that position is here. And so you end up with, this is where krypton is. And so silver is here. So you can see here that we're going to have this 5s2 and then 4d9. And you can see that based on where they are in the periodic table. Krypton, speaking of krypton, if you were to write out krypton, it would be this long chain, 36 electrons. And you'd have the 1s2, 2s2, and you can again see I'm following these diagonals. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And you can see I rewrote it so that the 3s and the 4s are together because you want those energy levels to be associated with the right energy level. And you will always see the D getting moved back inside because it is an interior protected valence shell. Periodicity. The F block of the periodic table belongs in the center of the periodic table between the S and D block. This is true. You can see here the lanthanide and actinide series put into the periodic table. You can see how long this makes the periodic table, so it really is easier for us to move it below because we do know that it belongs there and that the F orbital is going to be a protected orbital between S, P, and D blocks. On the following tiny periodic table, draw the trends and explain in words what is happening. I'm going to go ahead and show you all of these so that I can draw on it. It's given me some trouble with my program. So the ionization energy increases as you move to the right on the periodic table, and it decreases as you move down the group. So you would go up. So when you're looking at this ionization energy, the trend is going to go this direction because you want to know how it's increasing. like we saw in the previous video, it is how much energy is required to remove that first electron. And these at the top are going to hold on to them more. So because this helium only has 2, and the krypton, xenon have more electrons, it's going to be a little bit easier to remove that krypton xenon electron than it would be from the helium. For electronegativity, it increases as you go down the group, and it decreases as you go to the right in the period. So you're going to go this way, and you're going to go, for increasing, you're going to go this way. So the overall trend is from the top right to the bottom left. And how much an atom wants an extra electron depends on the distance from the nucleus and what shell is being filled. So it gets a little wonky here in the middle because those are variable in how they share and electrons. But as you go down, you're going to increase the atomic and ionic radii. Electronegativity increases as you move to the right in a period, so it's going to increase this way, and it decreases as you move down the group, so it's going to go up again. So the overall trend is going to be up and to the right. This one is I'm going to take that the atomic ionic radii. I read the wrong note. It is dependent on the number of protons that pull on the electron shells towards the nucleus. So that's why it's the size increases as you go down and as you move towards the left. The electronegativity is how much an atom wants an extra electron depends on the distance from the nucleus and what shell it's being filled. And then if you know the traits of some of the elements in a group, what can you do with the other members of the group? You can make predictions. So something in group 13, boron, acts a little bit different. It acts more like the nonmetals, but aluminum, gallium, indium, and they all act very similar to each other. And all of these are going to have very similar properties because of the number of electrons and the position in the shell that it's in.